In this video, we're going to talk how to apply modeling and optimization to select appropriate cloud platform for data warehouse workloads. Many organizations on premises, we call it on-prem, have data warehouses, data marts, big data clusters, running variety of the business workloads supporting different line of business. These workloads are growing. They experience increase in number of users and exponential growth in volume of data. It increases contention for resources and of course affect the cost. Many organizations are considering moving workloads, at least some of the workloads, from on-prem environment to the clouds. Our objective, our goal, is to apply modeling optimization to select appropriate cloud platform capable meeting service level goals in terms of response time for growing data warehouse workloads with the lowest cost. Different criteria can be used to justify cloud selection, including performance, scalability, deployment flexibility, database management functionality, etc. But we will use, during this project, performance, ability to meet service level goals, and cost. We'll review several major steps of cloud platform selection, including data collection and workload characterization on-prem and also on each of the cloud platform. This information is used to build a model and predict the minimum configuration which will be required to meet service level goals hour by hour, shift by shift, day by day during next 12 months. Predicted minimum configuration is used in order to predict the cost, how much it will cost to support growing business workloads, increasing number of users, increasing volume of data during next 12 months. Predicted cost is used in order to compare different cloud options and justify selection of appropriate cloud platform. Let's review results of data collection and workload characterization for on-prem and cloud environments. These results are used as input to the model optimization to determine the minimum configuration which will be required to meet service level goals for growing workloads. First of all, measurement data collected on data warehouse, production data warehouse on-prem. Graph in the bottom showing results of workload characterization. We see CPU utilization by different line of business during 24 hours during typical day. So the first step, data collection, workload characterization on-prem. The second step is data collection during proof of concept benchmark. This is benchmark based on selected queries and selected representative data set. So the same queries were running on-prem and each of the cloud platforms to compare CPU service time and kilobyte per request for the same queries in order to compare the impact of changes in architecture, DBMS optimizers on performance of the same type of queries. This information is used in order to build and calibrate our models. Build models predicting what will be the impact of moving workloads from on-prem to different cloud options. From all business workloads running on production data warehouse on-prem, there are 4 workloads were selected to be moved to the cloud. What is interesting that CPU utilization by these selected workloads during first shift at night, during daytime and nighttime, significantly different. So if cloud environment will be able to use different amount of resources to support all this workload during different shift of the day, organization can save significant amount of money. This graph showing results of the measurement data collected during benchmark tests on 3 different clouds. We see the impact of increasing number of concurrent users from 10 to 80. And when number of concurrent users is growing, throughput shown by bars is increasing. And the highest throughput achieved by Vantage, and lines of different color represent response time for each of the cloud. We can see that response time for Vantage has the best scalability and the lowest value. The results of data collection and workload characterization are used as input to the models to determine the minimum configuration which will be required to meet service level goal for each of the growing workloads. So first of all, we built Q network model of Teradata data warehouse production environment. Then several workloads were selected, and we built model of the Teradata Vantage, AWS Redshift, and Snowflake environments. Teradata Vantage model take consideration that Vantage has the same massively parallel processing architecture as Teradata on-prem. It has limited scalability but sophisticated optimizer and workload management TASM, allowing to change priorities, concurrency, and resource allocation for individual workloads. TASM allows to change level of concurrency for workload using excessive amount of resources. So with unconstrained environment, workload can use excessive amount of resources. But with constrained or limited number of threads or number of requests processed by the system, this type of concurrency limitation can delay, can increase response time for workload with this type of constraint, but allocate more resources for other workloads. So other workloads will have improved response time, but workload with constrained number of concurrent requests can have additional software delays. The same type of things happening with priorities. So increasing priority for one of the workload can improve response time for this workload, but other workloads can suffer. It improve throughput for this workload with increased priority, but throughput for other workloads can be reduced. When we model AWS Redshift environment, we took in consideration that Redshift has very similar architecture as Vantage. It's massively parallel processing architecture with multiple nodes processing concurrently requests submitted by application. Current architecture and implementation of Redshift has limited number of nodes. The maximum number of nodes which will be used in one data warehouse cluster is 128. Future releases of Redshift, which use Aqua as intermediate layer, a layer between computing nodes and storage, will offload CPU utilization from compute nodes and significantly improve performance for queries. But this information, technical information about Aqua, is not available, so we didn't model this scenario. Snowflake architecture based on usage of multiple virtual warehouses. And it allows automatically scale out, add additional virtual warehouse when required, or scale up, increase capacity of each virtual warehouse. We model several scenarios. One of them when all workloads moving to the cloud are running on the same virtual warehouse, they share the same virtual warehouse. Or another scenario where each application has dedicated virtual warehouse. So if you're going to move 4 workloads, we can create 4 virtual warehouses, and each application will run on isolated virtual warehouse, which reduce contention for the resources between applications. Queuing network models allows to answer very specific questions, like, for example, what will be the impact of moving workloads from on-prem environment to specific cloud? Or what will be the impact of increasing volume of data or increasing number of users? But our goal, not only to answer this type of questions, but to find the minimum configuration which will be required to meet service level goal, or find the optimal priorities for different workloads which will be required to minimize contention for resources and support workload growth without necessarily adding additional resources. So to answer this type of questions, we use optimization technology, which allows to run models multiple times, iteratively, and evaluate different options, and move to the most optimal set of parameters which help to satisfy service level goals without adding additional resources. So goal here is to use gradient optimization to run models multiple times and find the optimal workload management parameters and the minimum configuration which will be required to meet service level goal without adding additional resources. Let's review several examples. And let's assume that workload will be growing, or number of users will be growing with a rate of 12% per year. And volume of data will be growing with a rate 10% per year. And we will review example of predicting the minimum number of instances and instance type which will be required to meet service level goals for each cloud. Let's review modeling and optimization results for Vantage for the second shift and for the next 12 months. This example showing results of the modeling and optimization and finding the minimum configuration required for Vantage during second shift during next 12 months. So we're showing what type of instance will be required and when additional instances will be necessary, when upgrade will be required in order to support service level goals. We're also showing results of workload management optimization. This graph is showing performance prediction results and results of optimization, defining when additional instances will be required to meet service level goal for growing workloads. And this is service level goal. In this example, we should find the minimum number of instances and instance type which will be required to be sure that response time for all workloads, this is 4 different lines, each color represents different workloads. So after moving to the cloud, this is example when we defined minimum number of configuration. Then when workload will be growing and response time will exceed service level goal, we predict we will need additional resources, we'll need additional instances. So 4 times additional instances will be required during second shift during 12 months. And this is optimized workload management priorities for each of the workload which we're going to move to the cloud. We predicted what kind of relative priority will be required to meet service level goal without adding additional resources. This is summary of modeling and performance optimization for all business workloads which we're going to move to Vantage Redshift, and Snowflake. This is instance type which will be required. This is 3 shift, first shift, second, and third shift. And this is 12 months. So this number is showing us that 10 M4 16 extra large instances will be required after moving workloads to the cloud, and when additional instances will be required to support service level goals. So this table is showing results of the modeling and optimization, finding number of instances which will be required during first, second, and third shift in order to meet service level goal for each workload. Obviously, if you remember, CPU utilization by all this workload during daytime significantly higher than during comparing with nighttime and evening shift. And obviously more instances will be required to meet service level goals. So this is results of modeling and optimization, finding instance type and number of instances during first, second, and third shift during next 12 months, which will be required to meet service level goal for growing workloads. If you remember, we expect 12% workload growth during 1 year in terms of increasing number of users, and 10% increase in volume of data during next 12 months. This graph is showing predicted monthly cost of supporting expected growth for 4 workloads, which we're going to move from on-prem data warehouse to different cloud options during next 12 months. This information is used in order to make a decision which cloud is most appropriate for production workloads. We reviewed how modeling and optimization technology was used to predict what will be the minimum configuration required for each cloud to meet service level goal for growing workloads during next 12 months, and use these results to predict the corresponding cost. This approach of evaluating different clouds and selecting appropriate clouds can be applied to different cloud platforms. The same methodology, the same models, or similar models. But selection of the cloud is a very important, challenging step. After selection of the specific cloud platform, the next step is to apply performance assurance technology, also based on data collection, workload utilization, modeling, performance optimization, for managing production workload in the cloud, for making decisions about changing priorities, concurrency, resource allocation, taking into consideration architecture of specific cloud, availability of elasticity, and different rules which can be constructed and changed in order to take advantage of specific cloud architecture. Thank you. And if you have any questions, please forward to email shown on the slide, and we will be happy to answer.